Okay, so this is our second last unit. It's on polynomials. So all we'll have left to do after Christmas is sinusoidal functions. We're going to start today with just an intro to polynomial functions. You guys have seen polynomial functions definitely in grade 9. There's a whole unit on polynomials. And you probably still haven't talked a ton about that since, but you have talked about linear relationships and quadratic relationships in the last couple of years. Those are polynomials. We just haven't defined them like that, but that was always true. Okay, so today is just our intro. It's going to seem kind of long as far as pages, but a lot of it is calculator work. A lot of it is like a quick, short answer, so it shouldn't hopefully take us that long. So yeah, you guys have the schedule. So we'll get into an introduction to polynomial functions. So the first thing that I want to just quickly review is what a function needs to be, because to understand a polynomial function, we need to understand a function. It's a relationship between two variables which passes the vertical line test. So that means if you have a function that looks like that, it needs to be able to pass that vertical line test. Each point only needs, or each vertical line can only hit one point. So if you had a graph that looks like this, that actually, yeah, so this like vertical line passes more than one point, right? So this one would not pass the vertical line, so this is not a function. So no, yes. Okay, so we're just gonna go through like a couple functions that you guys have seen before. So this is a parabola. Okay, if I wanted to sketch the graph, there's lots of different things that we could do to actually figure out points on here. But in reality, I think the best way for us to do it is just do these things on our calculator. We're gonna get a really accurate view. We can do things really precisely. Okay, so I'm gonna just go in and punch this in. So 4x squared minus 12x plus 8. Okay, so that's what that graph looks like. So if I want to sketch it, when it says sketch, that means that we don't have to put it on an actual sheet of grid paper, but we do need to make sure that our intercepts and like kind of our maximums and minimums are at good points. Okay, so what I can see is I've got an intercept on the y-axis at 8. And if you remember from previous years, that constant is always going to be your y-intercept. So I know that my y-intercept is up at 8. And then from my calculator, it kind of looks like one intercept on the x is 1, one intercept on the x is 2, and we'll talk about how to verify that in a second. But my graph kind of looks like that. So it just drops really slightly below. I'm up at 8, and there's my sketch, okay? And we're gonna fill in a couple things on the sketch as we go along. So if we wanna write the domain, any polynomial functions, our domain is gonna be x is all real numbers, okay? And we write it in set notation saying, okay, x can be all real numbers. If we want to talk about the range, if we look at this quadratic, we need to figure out what that minimum value, because it's going to be everything, y is going to be everything greater than or equal to whatever that value is. Okay, and there's ways that we can do this algebraically, right? We could convert to vertex form, which would give us kind of that PQ coordinate, if you guys remember from last year. But honestly, I think it's just it's not worth the hassle to go through that, because we can do it on our calculator. So we're gonna go second calc, and what we're gonna be looking for is a minimum value. So if you wanna write this second calc minimum, that's how we're gonna find this. So I'm gonna hit minimum, which is 3, and it's gonna ask, kind of like an x-intercept, it's gonna ask for a left boundary and a right boundary. So what I need to do is give it a point to the left of this vertex, and then a point to the right of it, and then my guess needs to be there. So my minimum happens when x is 1 point, we'll call that 1.5 because it would round, and y is -1. So y, the lowest point this graph gets to is -1. So that means that it's greater than or equal to -1. Okay, What are the x-intercepts? We're going to do second calc 0. Okay, so I'm going to go second calc 0. And so again, it's going to ask for a left boundary. This time we want it to the left of that point of interception with the y-axis, or sorry, the x-axis, and then a right one, and then a guess. The really important thing is that we only give it one. So if I did my left boundary over here and my right boundary over here, there would be 2 intercepts between that, and my calculator would be confused. Okay, so I've got an x equals 1, and then second calc 0 again, my left bound, my right bound, and x equals 2. Okay, so that's kind of what we thought, and I'm going to fill that in for myself on my sketch. Okay, so my sketch should always have my x and my y intercepts, and if there's like a maximum or a min, I'm going to actually change that from that PQ. And I didn't actually record the p-value, but it has to be halfway between those intercepts. So it's going to be 3/2 and -1. Okay, the other thing that we could do is just kind of draw like an over and mark it like that if we didn't know the x value. What's the y-intercept? Remember that that is always going to be the constant. So y is equal to 8 in this case. What is the value of y when x is equal to 2? Okay, so we'd actually plug in an x is equal to 2, so y is equal to 4 times 2 squared minus 12 times, 2 plus 8. So 2 squared is 4, 4 times 4 is 16, minus 24 plus 8. That's 0, which makes sense because x equals 2 was one of our intercepts. That's this point right there. Okay, so y is equal to 0. What is the value of x when y is equal to 10? So that means we want to plug a 10 in. Okay, so what we could do is we could grab this as y1, and we could grab that as y2. So if I want to figure out where it's equal to 10, I'm going to graph a line at 10. I'm going to just change my window a little bit so I can actually see it. Change my y max to 15. Okay, so I can see that there's 2 intercepts there, and to do those, then I'm doing second calc intersect. Second calc intersect. It's just going to ask for my first curve, so it's on the parabola there. Second curve is y equals 10. Guess, it just needs to be closer to whichever one you're talking about. So I get 2 values of x, so x is equal to negative 0.158 blah blah blah, so 0.16. And then x is equal to, so again, I just need my first curve, my second curve. My guess needs to just be closer to this one this time. So x is equal to 3.16. Okay, so there's a bunch of stuff kind of as a recap for functions. And so hopefully this feels somewhat familiar, a little bit of graphing review, all that kind of stuff. Okay, so another example is this graph shows the height of a ball, so that's going to be the dependent variable because it depends on the amount of time that that ball has been in the air. Okay, so the height of the ball thrown from the top of the building in meters at any time in seconds. Okay, so we're going to use the graph to answer the questions. We want to know what's the height of the building. So if the building was here and then we threw it from the top of that building, that means the height of that building is 128. So h is equal to 128 meters. And we know that because it's the y-intercept. It's when that ball was released. At time 0 when it was thrown, it was at that height. This one, I got confused. I forgot that I made this time and not distance away from the building. So let's do how long has the ball been in the air instead. Okay, so at that point it goes up, it comes back down, and then it hits 0, the height of 0, so the ground, at 4 seconds. So t would be equal to 4 seconds, and we know that because it's the x-intercept, where height is equal to 0. What's the maximum height the ball reaches? So we're looking at this point here. We know that the height is the y-coordinate, so h would be 144 meters, and I'm always giving myself a unit. At approximately what time is the ball at a height of 100 meters? So this time we don't have an equation that we can put this into our calculator. So we're gonna just interpolate. So that's something that you guys did in grade 9. So what that means is I go from 100 meters over to this line, and then from that line I'm just gonna go as straight down as I can. And then I wanna decide, okay, how many seconds-ish is that? So I'm gonna say at about 2.7 seconds. And I use these little squiggly arrows to say it's about, or not squiggly arrow, squiggly equal sign. And then domain and range, so x is going to be between 0 and 4, right? Because that's the only time that the ball's in the air. So between 0 and 4, and it can equal both of those things. And we could have also used t there as well, because that's the variable that we gave that axis. So I guess I should have used t's, but oh well, domain is usually x. And then range, again, y, but we could use h for height. So my range is everything from 0 to 144. So the minimum to the maximum value. So 0, and it includes 0. So we could have used h. Okay, so again, that's just some stuff that we can do off of graphs, some things that we can kind of, if there's like some sort of application, some sort of relationship happening, we can read that. And so hopefully that feels somewhat familiar from previous courses. Now what we're going to do is look at what a polynomial function is defined at. And both of those equations, both of those functions that we just looked at are polynomials. Okay, so polynomial function is in this form. And it looks really ugly, but it's actually not that bad. Okay, so a to the n is some number, and then x to the n is an x with some exponent. Then we've got a to the n minus 1, it's just a number, and then x to the n minus 1. So if n was like 2, then this would be n minus 1, this would be x to the 1. So it would be like an x squared, an x, and then this guy might be a constant. So it just basically means that there's all sorts of different powers of x. N has to be a whole number, okay? So it can't be a fraction or a negative number or anything like that. That power, or sorry, that exponent has to be a positive whole number. X is our variable. And then the coefficients, the a values, are real numbers. So they could be decimals, fractions, pi, e, all sorts of different things. They just can't be like the square root of a negative number is basically the exception. Okay, so something like y equals x squared minus 6x plus 7, that fits this rule. We've got an x squared and then an x and then no x. Okay, so this would be the no x term. We've got different numbers in front. This is the same as a 1, and then a constant. Okay, so this is a polynomial function. In grade 9, you guys talked about the degree of the function. So the highest power on x determines the shape of the graph or how the polynomial is named. Okay, so they each have different names, and we'll talk about them. The leading coefficient, this is the number multiplying the term containing the highest power in the variable. And generally it should come first, right? The x squared should be before the x is before the constant, but it's not always like that, so we just want to watch out for that. It's going to determine what we call the end behavior of the polynomial. So we'll talk about what that means. Meaning it's either increasing or decreasing. So I'll show you that when we look at the graphs. And then the constant term is the term that has x to the power of 0, because x to the 0, anything to the 0 is 1. So that means it ends up having no variable. It's always going to be the y-intercept, okay, because all terms containing x, if we make x equal 0, all of those terms equal 0, so it's the only one left. Okay, so knowing that, now we're going to look at these functions and figure out, are they polynomials? Okay, so do they meet these rules? If they are, we're going to state the degree, the leading coefficient, and the constant term. Okay, so if it's not a polynomial, demonstrate why. This guy, we've got 5 minus 1 over x. This exponent on this x, because it's in the bottom, it's in the denominator, this means that we have a negative exponent on the x term. What that means is that is not a polynomial, right? Because if we look back up on the bullet points up there, n, the power on that variable has to be a positive whole number, right? Whole numbers start at 0 and go up. Integers are negative. These guys are not. This one, we've got 4x squared minus 1/3 x plus 8. So we've got an x to the 2, an x to the 1, and then a constant term. All of these numbers are real. They're fractions, but that's okay. This is a polynomial. So what we want to do is we want to talk about the degree, the leading coefficient, and the constant. And when I do this, I want to use colons, not dashes, because dashes can sometimes look like negatives. So the degree of this function is the highest exponent on my x, so it's a 2. My leading coefficient is the number that's multiplying the x with that highest exponent, so it's going to be a 4. And then my constant is the one that's not attached to an exponent, so it's going to be an 8. What the leading coefficient determines is whether it goes up or down. So we talked about how it has n behavior, or it determines the n behavior. If it's a positive, that means that this graph is going to go up towards the right. Okay, so if it's positive, it kind of essentially has a positive slope at the end. Okay, so we'll talk about what the opposite of that would be on this example. We've got 3x squared plus 4, that's a constant, minus 9x to the 6 minus x cubed. E is just a number. We talked about it really, really briefly in the logs when we talked about the logarithmic regression that your calculator can do, and the difference between a log and a natural log, that ln. So e is just a number. It's 2.71 some, doesn't really matter, but it's a number. So all of my coefficients are numbers. I've got whole numbers on my exponents. This one is a polynomial. Okay, so again, we're going to talk about degree, the leading coefficient, and the constant. So the degree, even though this one, it starts with a degree 2, we need to pay attention because this negative 9x to the 6 is actually our highest exponent. It just didn't come first. It should come first, but this one was not, just to show you that, hey, sometimes we got to look at the whole thing. So then my leading coefficient is the one attached to that x to the 6, so it's going to be a negative 9. And then the constant is that positive 4. Okay, so the fact that we've got a leading coefficient that's negative this time, that means that as the graph approaches, goes all the way to the right, it's going to go down to the right. Okay, so I'll show you guys what that means graphically in a second. If we've got f of x equals cube root of x, remember that that's the same as x to the 1/3. My exponent on this one is not a whole number. So that means that this is not a polynomial. Okay, so you can expect a question on that of like, which one of these is a polynomial, which one's not, that kind of thing. So if we look at types of polynomial functions, there's kind of 4 main types that we're going to look at in this class. Okay, so there's even degree functions on the on the left side, and then odd degree functions on the right side. So there's 2 of each. Okay, if we have just a constant function, okay, what that means, I'm going to draw us a graph first so you guys have an idea, is there's my x and y axis. My graph kind of looks like that. Okay, so what that means is my degree, so it might be like y is equal to 4. That might be what I just drew. My degree is actually 0 because there's no exponent here. It is just a constant. Okay, so the number of zeros is going to be 0. It doesn't touch the x-axis at all. And so examples would be like y equals 4, or y equals -8, or y equals, we could get crazy and do like y is equal to pi all the way across. Something like that. A constant graph is always going to form a horizontal line. Okay, it's going to just be a straight horizontal line. The next one that we want to look at is a linear function. So this is going to be something like y equals 2x minus 6. Okay, the degree on this one is going to be a 1 because this x has an exponent of 1. The number of zeros is generally going to be a 1. It's always going to be a 1 actually. So it could be something like that. Could be something like that, right? We see one x-axis or one x-intercept in each. Got one y-intercept, so we could have like y equals -7x minus 11. We could have y equals negative point, I guess I should write the 0.5x plus 17, right? Any sort of linear y equals mx plus b equation fits this category. So this is just going to be a straight line that's not horizontal. Okay, so it's going to be generally diagonal would be a good word to describe it. A quadratic function, hopefully you guys recognize this from last year. A quadratic function has a degree 2. Okay, the number of zeros is going to be 2 or 0 or 1, and we'll talk about what those mean generally, or what those can look like, but 2 is kind of the default. So examples, we'd have like y equals x squared minus 6x plus 7, or y equals x squared plus 4, or stuff like that. Okay, so any sort of quadratic equation that you could factor, that kind of thing. So examples are kind of most standard quadratic, might look like that, or you've got 2 x-intercepts, but you could also have a quadratic, it's going to go forever, you could have a quadratic that looks like this, so that doesn't actually touch the x-axis at all, and that's okay. You could also have a quadratic that just touches at one point, so that's how we would get the 1 intercept or the 0, but generally we're going to see stuff with 2. Okay. Cubic function, so we went degree 0, 1, 2, cubic is 3, something cubed. The number of zeros is generally going to be 3, but could be 2 or 1, and again, that's kind of an exception. So examples would be like y equals x cubed minus 6x squared plus 17x minus 11. So I'm just making up numbers. That's a cubic function, okay? Generally what it's going to look like is boom, 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 something like that, okay? Or maybe like a standard, if we just had y equals x cubed like this, it actually looks like that. So if you just graphed y equals x cubed, that's one of those instances where it only has one intercept, and we'll talk about how that intercept looks a little bit different. There's like curvy bits to it instead of just straight through, so we'll talk about that tomorrow. Okay, so, oh, I forgot to name these two. This one is always a parabola, which hopefully looks familiar to you from last year, and this one, there's no real name for it, but it's curvy. They're curvy lines, okay? So there's kind of the general functions, okay? So there's some patterns here with odd and even degree functions. If you guys can see this is hard because I can't, I'm going to zoom out a little bit. So on both my odd degree functions, notice how one end goes up and one end goes down. One end goes down, one end goes up. One end goes down, one end goes up. One end goes down, one end goes up. That's always going to be true. So for odd degree functions, your domain is always going to be all real numbers. Your range is always going to be all real numbers. So I wrote that up there. We'll get into that a little bit more as we keep going. Our even degree functions, they go forever left and right. Okay, so this one, all of these guys, they all go forever left and right. So my domain is always, again, x is equal to all real numbers. But my range is either something really specific or something that stops at a specific point. So if we think about a parabola, our range here is either like, let's say this was like -6. This would be y is greater than -6. Or let's say this is -5. Y is less than -5, or y is less than 0. So our range is less than or greater than some sort of value. Okay, so it's going to be something a little bit more specific instead of everything. It doesn't go up or down. Like one part doesn't go up and one part doesn't go down. They both go the same direction because of that like parabola shape. So we're going to actually do some of this. We're going to practice kind of recognizing these things that we just talked about. Okay, so this one has an x to the 1, so that means it's a linear function, right? Degree 1. 1 is odd, so remember that means it's going to be spanning both things, both directions. So x is all real numbers and y is all real numbers. And this is always true for odd degree. Okay, so odd degree functions. My leading coefficient, remember, is the number attached to the highest degree term. So that's this 7. And that means it's going to go up towards the right. Okay, so if that leading coefficient is positive, it's going to go up as we move towards the right. My x-intercept is, I can solve for it. So I could plug in x-intercept happens when y is equal to 0, so 7x minus 5. So then if I add 5 to both sides, I'm going to get, x is equal to 5/7. And if you did that graphically, that would also be okay. The y-intercept happens when x is equal to 0. So 7 times 0. That y-intercept, as we said before, is always going to be that constant value. So y is equal to -5. So if I wanted to sketch a graph of this thing, without doing it on my calculator, I can. But honestly, I think just doing it on your calculator it's a more sure way to get it right every time. Okay, so if I wanted to use f at 0, that is my y-intercept. So that's -5. I know this is going to be -10, -20, +10, +20, because I know that this kind of spans. So that y-intercept happens kind of halfway between there at -5. Then if I wanted to graph f at 2, that means I'm just plugging a 2 in for x. So I guess I should actually start with 7. So 7 times 2 minus 5. 7 times 2 is 14. So we get a 9. So if x is equal to 2 there, it's going to be right below that 10 spot. And then f at -2, -14 minus 5, so -19. So if there's -2, it'd be kind of down there. So see how we've got that linear function. It's going up to the right because my leading coefficient's positive. it's hitting my y-intercept or my y-axis at -5. My x-intercept, see how that kind of looks? It's closer to 0 than it is to 2 because it's a little bit less than 1. There's my 5/7. Okay, but I could confirm all that. I could just graph this in my calculator if I wasn't sure. Okay, what solve f of x equals 26 means is that the value of the function, or the y value, is equal to -26. So I'd plug that in as the y value, or the value of the function, the value of f of x, and that would have to equal 7x minus 5. And so I'd be solving for the x value that makes that true. So then I have to add 5 to both sides. Divide both sides by 7. So x would be -3. Okay, so this is just lots of different things that we can do with these functions. This one, we've got 2 more examples left. I know this one's a little bit longer than normal, so my apologies, but the next couple are a little bit shorter, so it's just today that's quite long. So this one, we've got the type of function. See how we've got a degree 2? That means this is a quadratic function. Let me know that again because it's degree 2. So the even or odd degree, 2 is an even number, okay, which tells us that my domain is all real numbers, but my y is going to be less than or greater than something. And to figure out what symbol needs to go there, we could either graph it or we can look at a couple other things. So before I graph it, we're going to think about our leading coefficient and what that means. So my leading coefficient is -1, right? It's a -1 multiplying that highest degree term. So what that means is that my parabola is going to go down to the right. So if we kind of think about that, it's going down to the right. Then if I extend it backwards to the left, it would have to peak at a point and then go down to the left as well. So it would be opening down. So if you remember from Math 20, that leading coefficient being negative means that it's like a sad face parabola, right? We see this sad face. So that means that y is going to be everything less than or equal to a specific value. And at that point, we could calculate based on the axis of symmetry or convert to vertex mode, but you have your calculator, so I just want us to know how to use them really well. So we're just going to plug it into our calculator. And we would be able to then see, hey, is my domain right? Hey, like, we can just read this range off the calculator. So I'm going to go in, and I'm going to graph -x² minus 14x minus 40. I'm going to hit graph. Okay, so there is my parabola. Okay, I want to know what that peak value is, so I'm going to go second, calc, and this time I'm looking for a maximum. So I want number 4. My left boundary, I need to kind of scroll until I get that in screen. So I want a maximum value between kind of here and here, right? My max is there, so I'm going to give it left boundary, right boundary, and then a guess. So my max is basically -7 for x, and y, that's what we care about. That y coordinate is at 9. So that means my range is everything less than or equal to 9. The x-intercept, same deal. We could factor this thing, but we have our calculator, so we're just going to do it second calc 0. So again, left bound, right bound, guess. We get an x is equal to -4. Do my other one. I might have to change my window here a little bit. I've already done it. It's x is equal to -10. Okay, we can kind of see it. It's like right on the edge there. And if we thought about the factors, 2 numbers that multiply to 40 add to -14, or I guess we'd have to divide everything by so if you wanted to factor, it would look like this, because we'd want that positive number to be there. Oops, you can't see that. But yeah, two numbers that multiply to 40, add to 14, it's 4 and 10. So there's my two numbers. Okay, so we just did this graphically, but we could vector. The y-intercept is just my constant, so it's going to be negative 40. Okay, so my constant is that negative 40. That's always going to be my y-intercept. So if I wanted to draw a picture of this using the intercepts in the range, I know that I've got an intercept at, so if there's negative 10, there would be negative 4. My range goes up to positive 9, so that's my middle point. And then if I draw this as accurately as I can, this looks kind of like it's almost 4 times lower than this is, right? So there's my y-intercept of negative 40. Okay, so again, we see that leading coefficient being negative, it's going down to the right, and that's always going to be true. This last one, so this is cubic. This is probably the least familiar for us. We see that x cubed, this is a cubic function, which means it has degree 3. 3 is an odd number, so this is an odd degree function. My leading coefficient is a 1, right? So it's just 1x cubed, which means it's going to go up to the right. My domain, so remember how we talked about odd functions? X is going to be real, all real numbers, always. Doesn't matter if it's even or odd. And then range, oops. Y is going to be all real number, and that's always for odd functions. One's going to go up, one's going to go down, so it's going to hit kind of like that, right? So it might look like that somehow. It got a little bit slanty, whatever. Yeah, like that. Okay, my x-intercept, okay? To do this, we're going to just graph it. There's a way that we could figure it out algebraically, but it would take a whole different lesson, and we've just been doing everything graphically, kind of on purpose. So x cubed minus 3x minus 1, and I graph it. I've got 1, 2, 3 x-intercepts. So we go second, calc 0, and we need a left bound and a right bound. This one we got to be real careful with, so left bound just to the left of it. The right bound kind of has to be on that peak. So I get x is equal to negative 1.53. Okay. The other two I've already done just to save us a little bit of time. You're going through that same process. X is negative 0.35. So you can see how another one is just to the left of that y-axis, so another negative one. And then x is 1.88. So I just rounded them all to the nearest hundredth, which is kind of standard if it doesn't say what to round to. My y-intercept, I could do it on my calculator. I could figure out what that value is, but remember that y-intercept is always going to just be your constant value. So in this case, it's a negative 1. And we can see that on our graph. It's right there. Then if we want to graph using technology, hey, we already did that. So it looks like, and when we sketch this, we want to kind of be as accurate as we can. So there's negative 1, there's my 2 x-intercepts. It goes down below that and then comes back up. Okay, so there's negative 1.53, there's negative 0.35, there's negative 1, and there's 1.88. Okay, and then as we talked about, because of my positive leading coefficient, it's going up to the right. Because of the fact that it's an odd function, my y spans both directions up and down forever, so all real numbers. My x spans both directions, left and right, so all real numbers. I probably shouldn't have drawn that. I feel like it was confusing, sorry. Solve f at 2, that means we're plugging in x is equal to 2 into the equation, so f at 2 is equal to 2 cubed minus 3 times 2 minus 1. So we're plugging in that x equals 2 and figuring out the value at that x value. So then 8 minus 6 minus 1. 8 minus 6 minus 1 is, oops, 6 and 1 is 7. That's just 1. So at a value of 2, this thing would be at a positive 1 value. Okay. And again, we could actually figure that out. We could go and say, okay, second calc, insert a value, x is equal to 2, there's my y is equal to 1. So we could check that graphically. Okay, so I know that one was longer. It was, I think, like mostly review as far as calculator stuff, domain and range, just kind of going over stuff that we've known a little bit. The big stuff for today are the names of the functions, that even and odd degree, how to identify that, what the leading coefficient means, okay, whether it's going to go up to the right or down to the right. So kind of the big stuff to focus on for today is how we can figure these things out without actually graphing it, okay? But you're always going to have your graphing calculator. So we want to understand kind of the patterns here, but you can always, 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 if you get confused, use this. Okay, so in your snap book, there's a bunch of practice problems that just go over this. Most of them, they're going to be graphically, right? So if it's saying, what are the intercepts? What's the domain and range? You can always graph that picture first and then go from there. If you have any questions, let me know.